Hey guys, Mr. Record here. In this video, we're going to wrap up Chapter 9 in the Larson textbook with the topic Taylor and Maclaurin Series. It's quite likely that if you're watching this, you may have already done some experimentation with Taylor and Maclaurin polynomials. We're just going to take that to the next level here and build a series, a power series out of a very popular function. The Larson book begins with this theorem 9.22, the form of a convergent power series. I apologize for the spelling error there. Let's cross that C out. There we go. The form of a convergent power series. And it basically harkens back to the formula that you have been taught that deals with the building of a Taylor or a Maclaurin polynomial. So if you take a look at this thing, it probably looks very familiar. You know, we're building term by term by using the fact that we begin with the f evaluated at c, build towards the derivative evaluated at c, and the second derivative, and so on and so on. And then we have to remember that we've got these various denominators that match the derivative that we've taken to a factorial. Of course, the first couple won't be written. And then, of course, you finish up by taking your value of x. If it's centered somewhere other than 0, you would subtract that centering, and then you would raise it to a power that matches the derivative that you've taken. So this is nothing new. What's new about this is the fact that we are going to build this on and on and on and make a series out of it rather than a polynomial. So we now have this formal definition then of a Taylor or a Maclaurin series that just utilizes the information of theorem 9.22. And really our goal is to get something real tidy and neat that looks like that. Okay? Once again, I can't iterate this enough. Think of a Taylor or a Maclaurin polynomial as possessing a finite number of terms, whereas a Taylor or a Maclaurin series will possess an infinite number of terms. And we have learned that for most of these kinds of series, or functions, I should say, that we talk about, the more terms that we can generate, the more reliable that they are. Well, here is our example 1. We're going to use the function f of x equaling the sine of x to form the Maclaurin series as detailed by our definition above. And the last thing we want to do is determine its interval of convergence. So I'm going to start a fresh page here, and we'll get working on this. It's, again, very likely, depending on how much experience that you have with building Taylor-Maclaurin polynomials, Taylor-Maclaurin series, you might have the sine of x memorized. And if you do, that's fantastic. I would always advise to any students who are going to take the BC Calculus exam, if you can memorize a few of those nice little power series, it will save a little bit of time. But it's not that big of a deal if you have to develop one. You just have to work a little quickly, work accurately at the same time, and you shouldn't have any trouble getting that power series developed. So let's assume that a student doesn't quite remember what the series is going to be or what it's going to look like. So you would first of all start with the general facts, the fact that f of x is indeed sine of x in this problem. And then you would just proceed to take a number of derivatives. The first derivative being cosine of x, and the second derivative being negative sine of x. The third derivative would be negative cosine of x, etc., etc. Now, it's easy to wonder, hey, when do you stop? Well, I always tell my students, you stop whenever you feel like stopping. As long as you have been able to, or will be able to develop some kind of a pattern, you've got as many derivatives as you're going to need. So after this, we're going to evaluate each one of these at where we're centered. And in this particular case, since this is a Maclaurin series that we're about to build, we would be centered at 0. So I'm going to go ahead and find out what each of these is going to equal. Well, the sine of 0, of course, is 0. The cosine of 0 is 1. The sine of 0 is 0. Negative cosine of 0 is negative 1. Sine of 0 is 0. And back to cosine of 0, which is positive 1. And if you've dealt with the building of the sine function, this might ring a bell in the fact that you do seem to miss some terms and you do have this alternating sort of idea going on. So if we were to take these guys right here, and if we were to write down what is the series going to build, what is it going to look like? Well, we would start with, of course, f of 0, which is 0. Not much happening there. And then we will add to that f prime of 0, which is 1, multiplied by x. Then we would have f double prime of 0, which is, of course, 0, multiplied by x squared, all divided by 2 factorial. And then we would proceed to have plus f triple prime of 0, which is negative 1, multiplied by x cubed, all over 3 factorial. Then we build up to the fourth derivative. That would be this value here, 0, multiplied by x to the fourth, over 4 factorial. And then we have our fifth derivative, 1 multiply by x to the fifth, over 5 factorial. And as we said, this pattern would continue. We would continue in this same vein. But I think that we definitely have enough terms to start giving ourselves an idea about how we could write this as a power series. Of course, any term that contains a 0 will not be written. Everything else we're just going to simplify. So we'd start, of course, with 1. And then we see that this term here could become negative simply x cubed over 3 factorial. It's going to probably help to write your denominator still in factorial form. And then we have our fifth degree term, x to the fifth over 5 factorial. And it's highly likely that you could probably guess the next couple of terms. Just by seeing the pattern here, the alternating sign taking over, the fact that our exponents of x are going to be odd, and that that exponent will match the factorial value in the bottom, it's a pretty safe bet that your next couple of terms might look like this. But where we would stop a few sections ago when we were dealing with finding a Maclaurin polynomial would be somewhere here. Do we want the 5th degree, the 7th degree, the 9th degree? Well, we don't want that anymore. We want a full-blown series for this. So now our job, after we've got this sort of Maclaurin polynomial written, we want to really be able to turn this into a nice, tidy Maclaurin series so that it will be equivalent to the sine of x. So now that we've got this nice Maclaurin open form polynomial written, we're going to try now to go ahead and write it so that it will be equivalent to the sine of x, but look more like a power series. And that really won't be very difficult because we just have to recognize some patterns here. First of which, we know that this is an alternating series, so it would have that alternating component -1 to a power. And seeing as how our first term, when n equals 0, is a positive, it seems logical that would put an n for the exponent of -1. And of course, we'd have an x that follows close behind with an odd exponent, 1, 3, 5, 7. The universal way to say that odd value would be a 2n plus 1, of course. And then the denominator will also be a 2n plus 1 because of the fact it would match the exponent. So this turns out to be our power series. I got to be a little bit careful before I say unequivocally it's definitely equal to the sine of x, because it's only going to equal to the sine of x on the interval for which it converges. So we have some more work to do with this. We're going to have to now focus on finding out what the interval of convergence is. And since this is not a real basic type of geometry power series, we'll probably have to use our good friend, the ratio test. No doubt you guys have used the ratio test if you're watching this video. And the ratio test simply says to take a good look at the nth plus 1 term. Now, the nth plus 1 term here would cause for us to take this n value out, replace it with n plus 1. We would have 2n plus 2, and then add the other 1 to get the 2n plus 3. And we have the same thing happening here in the denominator. Then we would divide this by an, or multiply it by the reciprocal of our original nth term expression. So now I'll give you a moment to let that all sink in as I focus on our next step, and that will be to perform some algebra so that we can simplify this thing. So this limit would then become, well, the negative 1 to the n plus 1 and the negative 1 to the n will reduce a bit to just give us a negative 1 to the first. And the x to the 2n plus 3, I could subtract exponents, 2n plus 3 and 2n plus 1, and I would end up with a square, a 2. And then as far as the factorials are concerned, I know I've worked with my class on these for a few problems, but basically this 2n plus 3 factorial contains a 2n plus 1 factorial a couple of terms before, and then what would follow that 2n plus 1 factorial would be the multiplication of 2 more terms, namely 2n plus 2 and 2n plus 3. All right, now we're ready to take this limit, and we find out very quickly that if we isolate in on just the values here in the denominator, this negative 1 is really going to go away because of the absolute values. The x has very little, if nothing, to do with the limit process because he doesn't contain an n. And we can see that having an n squared value in the denominator and no n's in the numerator is definitely going to give us a limit of 0. And it really doesn't matter what the absolute value of x squared was going to be. For any value of x, this limit is going to be 0, period. And because 0 is definitely less than 1, then we have a situation where we have convergence. No matter what this value of x is, x can be anything in this power series. We are going to get a limit of 0 for our ratio test. So that will say to us that the interval of convergence for sine of x power series is everything. You could write that a couple of different ways, in interval notation or, of course, inequality notation. And it's really nice whenever you have this result and that you do not have to check the endpoints. So I guess the final answer here will be what I've written above with this new interval notation, and we'll go ahead and kind of box that in so we don't lose it. But I'd like to show you something else with this. I'd like to show you graphically really what's happening here. And any graphing calculator will certainly do this. I'm going to use the TI-Nspire, and I think I can do this pretty easily on a graph page. What I like to tell my students is to first of all go ahead and sketch the power series first. So we would use the summation, and we're going to take the summation as n goes to 0, or starts at 0, and I'm going to worry about the upper bound here in just a little bit. But finishing off, we've got a negative 1, let's see, to the nth power, and that will be multiplied by what was it, x, I believe it was x raised to the 2n plus 1. And then we will divide all of this by the factorial value of 2n plus 1. On the TI-Nspire, the factorial is located in the punctuation key. And then I kind of left this upper bound b for just a moment. You've got to be very careful working with virtually any type of computer or graphing calculator, because if you put infinity up there, you might want to make sure you've got a lot of free time on your hands, because it's going to cause the computer or calculator to work quite busily on that particular power series. And what I have found that works very nicely, especially with the handheld, is using, say, it's something like 25. It might cause the clock to appear on your Nspire for just a little bit, but not for any uncomfortable amount of time. And you'll find out in this particular case with the computer software, it'll graph pretty quickly. And it probably graphs something that you're a little familiar with. Yeah, does that look a little bit like the sine of x? Well, we can easily find out by opening up our entry line again and actually physically putting in sine of x. Since I'm using the TI-Nspire CX here, I would end up getting a graph of a different color, and it looks as if that red graph of sine of x seems to align very nicely with this blue graph that we've had. Another way to really see what's going on here is using the table Control T, and I can kind of slide this pane over a little bit, hopefully, and make this a little bit wider, if it's going to let me. Oh, it's not going to let me. I'm in a scratch pad. No big deal. I can easily fix that. I'm going to go ahead and make this a new document real quickly. All right, now everything's the same. I just will now be able to slide this over, and we can find that we have the values in our our blue column for the power series and our red column for the sine of x to be spot on, term for term for term. And we could continue to do this on and on and on and on, and it really isn't going to be very surprising, because we have found that the interval of convergence was indeed negative infinity to infinity. So anyway, I hope that helps, and we'll see you next time.